Ever feel like the tech landscape is just moving so fast? It's like trying to drink from a fire hose,
Yeah,
right?
definitely.
You want to stay informed, but, who has the time to wade through everything?
It's a real challenge.
That's exactly why we do the Dup Dive. We take your key sources, research, notes, those vital articles, and, well, we pull out the crucial bits.
The nuggets of knowledge.
Exactly, giving you that shortcut to really knowing what's going on, maybe finding some surprising things along the way.
And for this deep dive, we're looking at Article 11 from an RHCSA series. It gives a really rich overview of 5 advanced GNU Linux features.
Yeah, the stuff that really powers so much of modern computing.
Totally.
Okay, so our mission today, unpack these 5 areas. We're talking clustering, specialized storage, virtualization, cloud computing, and real-time computing.
Heavy hitters.
Right. By the end, you're going to have a really solid grasp on why GNU Linux is such a beast in today's world, from huge data centers right down to critical industrial controls.
Okay, let's do it.
Let's unpack this. So, first up, clustering. When you think about these massive websites, streaming services, banks, how do they stay online and fast? With millions of people hitting them, it can't just be one giant computer.
No, definitely not. That's where clustering comes in. And the source breaks it into 3 main ideas. First up is high availability clusters, HA clusters.
HA.
Right. These are all about keeping mission-critical systems running. No downtime allowed. The key is redundancy.
Redundancy meaning?
You have multiple servers basically running identical copies of everything, the applications, the services.
Okay.
And the clever part is if one server fails, another one automatically takes over.
Yeah.
Instantly.
Like a seamless handover, a baton pass.
Exactly like that. The user shouldn't even notice. There are tools like Pacemaker, which sort of orchestrates this failover,
Right.
and CoroSync, which handles the communication between the machines in the cluster securely.
Okay.
And they often work with things like DRBD, that's distributed replicated block device, to keep the data perfectly in sync.
So the backup machine has the exact same data ready to go.
Precisely. And best practices usually involve shared storage like NFS or ClusterFS, and really careful network setup so they can talk constantly.
Makes sense for keeping things up. But what about keeping things fast when, traffic just explodes?
Good question. That brings us to the second concept, load balancing.
Okay.
This is all about spreading the incoming traffic, the requests, across all those servers in the cluster.
Smartly.
Like a traffic cop for the network.
Yeah, pretty much. It stops any one server getting totally slammed. Directs traffic to the least busy one, or maybe one that's better suited for that specific request.
And the benefit is?
Big performance boost. Much faster response times for users, and overall the service stays way more available because you don't have bottlenecks.
What kind of tools do that on Linux?
Well, common ones are HA proxy. That's really good for TCP and HTTP traffic. And Jinx is huge too, often used as a web server and a load balancer.
Right, I've heard of Nginx. Yeah, it's everywhere. And then there's LVS, the Linux virtual server, which is really powerful for handling massive amounts of traffic.
So load balancing keeps the lanes moving smoothly. But what if the job itself, the actual computation, is just too massive for one server, even a fast one?
Ah, okay. That's where distributed computing comes into play.
Right.
This lets you run applications across a whole group of connected computers. They act like one giant brain, basically.
Pooling their power.
Exactly. You get increased processing power, you get jobs done faster, and it scales much better for really huge tasks.
Tasks that would just crush a single machine.
Right. It's also much more efficient with hardware resources, and it gives you fault tolerance. If one computer in the group fails mid-task, others can often pick up its work.
Are there specific frameworks for that?
Yeah, the source mentions things like MPI, which is common in scientific computing for parallel jobs. Hadoop, famous for big data processing.
Right.
And Grid Engine for managing these distributed workloads across lots of machines.
Wow. So, okay, wrapping up clustering. What's the big takeaway if you're building systems that need to be super reliable and handle heavy loads?
Then understanding these clustering concepts, HA, load balancing, distributed computing, it's foundational. It's how you build things that, well, just don't quit.
But it sounds like it adds layers of complexity, right? Are there common pitfalls?
Oh, absolutely. Managing that data consistency across nodes, making sure failover actually works when you test it, even just debugging, it gets complicated fast. You need solid planning, and really good monitoring.
Right, it's not just plug and play. Okay, so once you have these systems working together, they're generating and using tons of data. Where does it all live?
Exactly, which brings us to specialized storage.
Yeah.
And yeah, this is crucial for anyone drowning in data. The source highlights three main types.
Okay, what's first?
First is network-attached storage, NAS.
NAS. Okay, I think I've seen those boxes.
Yeah, probably. Think of it like a shared network drive, a central digital filing cabinet everyone on the network can access. It's file-level storage.
Meaning you see folders and files, like on your own computer.
Exactly. Just shared over the network. The Thor says it offers easy access, and it's really good for small to medium-sized businesses.
For what kind of tasks?
Regular stuff.
Yeah.
Sharing documents, streaming media internally, backups. It's generally high performance enough for that. Scalable, pretty flexible.
Okay, so NAS for shared files. But what about things needing really high speed, like big databases or those virtual machines we'll talk about later?
Right. For those, you're often looking at storage area networks.
ANSYNs.
ANSYNs. How are they different?
They provide block-level storage connectivity. So instead of seeing files, the servers see raw storage blocks, almost like a directly attached hard drive, but one that multiple servers can share access to.
Ah, so more direct, lower-level access.
Exactly. If NAS gives you the whole book, NL lets you grab specific pages or paragraphs directly.
Yeah.
It uses dedicated high-speed interfaces, things like Fiber Channel or RHCSA.
And that direct block access means better performance, better scalability, better availability for those really demanding large-scale applications.
Yeah.
Databases, virtualization environments, where speed and direct control are key.
That file level versus block level distinction seems pretty important. NAS is the network drive. SAN is more like a shared raw disk.
That's a good way to put it.
But what about data that doesn't fit neatly into files or blocks? You know, like billions of photos, videos, log entries, that kind of unstructured stuff?
That's where object storage systems come in. They are built specifically to handle massive amounts of unstructured data efficiently.
How do they work?
Instead of files or blocks, they store data as objects. Each object is a self-contained unit with the data itself, a unique ID, and metadata describing it.
Okay, like a little package.
Kind of, yeah. This makes them incredibly scalable, flexible, and cost-effective for managing huge volumes of content. Think multimedia archives, endless logs, long-term backups.
Any examples on Linux?
Sure, open source ones like Ceph are really powerful. It can do object block and file storage. And then there's Swift, which is well known specifically for huge-scale object storage.
Interesting. So 3 different approaches.
Which definitely raises a key question. With such distinct methods, how do you pick the right one? Choosing correctly is critical for performance and managing your data well.
Yeah, it sounds like you really need to know how you'll access your data and how much you have. Otherwise, you could end up with the wrong tool for the job. Could be an expensive mistake.
Definitely. Understanding those access patterns is key.
Okay, moving on. Virtualization. This feels like one of those concepts that just changed everything in computing.
Oh, absolutely.
The idea of running multiple, completely separate computers on just one physical box, it's still kind of mind-bending.
It really is. And the benefits are huge flexibility, using your hardware way more efficiently, keeping different workloads separate.
So how does it work?
Yeah.
The source mentions 3 main flavors.
It does. First is full virtualization. This is where the system completely simulates the underlying hardware.
Like a perfect imitation.
Pretty much. It means you can run unmodified operating systems as virtual machines. Windows on Linux and other Linux on Linux, whatever. They think they have their own physical machine.
And on GNU Linux, how's that done?
The big one is KVM kernel-based virtual machine. It's amazing because it's built directly into the Linux kernel, which makes it fast and efficient. It uses the CPU's own virtualization features. KVM often works with QEMU, the quick emulator, which handles emulating specific hardware bits, network cards, disk controllers, that sort of thing. Together, they give you really powerful and flexible virtualization setups.
Okay, so full virtualization is separate OEs in one box. But sometimes you don't need a whole separate OS, right? Just the app.
Exactly. And that's where containerization has exploded in popularity. It's a different approach.
So.
It isolates applications and their dependencies within containers, but crucially, it doesn't virtualize the entire operating system. All the containers share the host OS kernel.
Ah, so much lighter weight.
Way lighter, much lower resource use. Containers start up almost instantly. Docker is the one most people know, famous for its simplicity and vast ecosystem.
Right. Docker images, Docker Hub.
Yeah. But there's also Podman, which has gained a lot of ground. It's seen as a more secure, daemonless alternative, often preferred in enterprise settings, partly because it can run rootless easily.
Interesting. So full VMs versus containers. Is there anything in between? I feel like I've heard of another type.
You probably have. That would be para-virtualization.
Para-virtualization.
Okay, this one's a bit different. It needs a modified guest operating system. The guest OS knows it's being virtualized and can talk more directly to the hypervisor, the software managing the VMs.
Why modify the OS?
That direct communication can lead to better performance than full virtualization in some cases. You cut out some of the emulation overhead. Zen is a very well-known para-virtualization platform. It's been around a while, used in demanding robust environments where squeezing out performance is critical and tweaking the guest OS is okay.
Gotcha. So it seems like you have this spectrum: full isolation with VMs, super lightweight app isolation with containers, and as somewhere in the middle, focusing on performance.
That's a good way to think about it.
So for anyone listening, developers, sysadmins, these tools give you incredible options to balance performance, flexibility, security, really optimize your setup. But it also makes me wonder, what's a common mistake people make choosing between, say, a container and a full VM?
Yeah, a really common trap is just defaulting to containers because they're trendy or lightweight without thinking about the actual need. If you truly need kernel-level separation, or you have an app that absolutely must run on a very specific older OS version, a full VM might still be the only way. Or the opposite, running lots of tiny, simple web services inside full VMs when containers would be way, way more efficient.
So it's about matching the tool to the actual workload, not just the hype.
Precisely. Understand the isolation and resource needs first.
Okay, that makes perfect sense. So we've gone from one machine running many virtual ones. What about when the machines aren't even yours? Let's talk cloud computing.
Right, the next logical step.
It's reshaped everything.
Yeah.
How does GNU Linux fit into powering this massive global infrastructure that delivers services whenever we want them?
Well, Linux is basically the foundation of the cloud. The source breaks cloud down into three key service models. First is infrastructure as a service.
IS.
IS.
Like renting the hardware.
Essentially, yes. It provides virtualized computing resources over the internet. Things like virtual machines, storage, networking. You rent the basic building blocks.
And Linux's role, it's huge. Linux-based systems are widely used to power IaaS platforms. Why? Because Linux is seen as reliable, secure, and flexible. It lets users quickly deploy servers without buying or managing any physical kit.
Okay, so IaaS gives you the raw infrastructure, but maybe you don't even want to manage operating systems. You just want to code.
Then you're looking at Platform as a Service, or PaaS.
PaaS.
This offers a complete development and deployment environment in the cloud. It handles the infrastructure, the OS, the patching, the networking, everything below your application.
So developers can just focus on their code?
Exactly. Freeze them up completely. Focus on writing and deploying applications. And again, GNU Linux is very often the foundation for many PaaS solutions, supporting all the popular languages, databases, you name it. Think of services where you just push your code and it runs.
That sounds incredibly efficient, but when you're operating at cloud scale, thousands, maybe millions of VMs or containers, how do you manage all that complexity without an army of people?
That's where cloud orchestration is absolutely vital.
Orchestration. Like a conductor. Kind of, yeah. It's the automated management of cloud resources, coordinating everything, VMs, networks, storage, containers, automatically and efficiently.
What tools do that?
Well, for managing large-scale infrastructure, especially in private clouds, OpenStack is a major open source player.
Okay.
And for containers, Kubernetes has pretty much become the standard. It handles automating the deployment, scaling, and management of containerized applications. It's incredibly powerful.
Kubernetes, you hear that name everywhere now.
You really do. And connecting this back, these orchestration tools, along with IS and PIAs built largely on Linux, are why the cloud is so efficient, reliable, and scalable. It's transformed how businesses operate.
It definitely seems like the default now, but are there still good reasons to keep your infrastructure in-house on your own Linux servers, maybe for security or cost?
Absolutely. It's not always cloud or nothing. For super sensitive data or industries with really strict regulations, keeping things on-premise might be necessary or preferred. Also, if you have very predictable, stable workloads, the long-term cost of owning and running your own gear can sometimes be cheaper than perpetual cloud subscriptions. And some specific high-performance computing tasks might just run better on carefully tuned, dedicated hardware you control completely.
So it's still a trade-off. Control versus convenience, cost models.
Exactly. It's an analysis you have to do based on your specific needs.
Okay, let's shift gears one last time. We've talked scale, flexibility. What about speed and predictability? Situations where timing is absolutely critical.
Ah, yes. Real-time computing.
Right. Where milliseconds matter. Any delay, any unexpected pause could cause major problems. Think industrial controls, power grids, maybe telecom systems, robotics.
Critical applications, definitely.
How does standard GNU Linux handle that? Or does it need something special?
It generally needs something special. Standard Linux is optimized for overall throughput, fairness, getting lots of things done reasonably quickly. Real-time needs guaranteed timing. The source points to 3 key things. First, real-time kernels.
Special versions of the kernel.
Exactly. Specially modified versions of the Linux kernel that prioritize time-sensitive tasks. They're designed to minimize delays, ensure high-priority stuff gets CPU time immediately. They aim for guaranteed response times.
How do they do that?
Techniques like preemption are crucial, allowing a high-priority task to interrupt a lower-priority one instantly, much more aggressively than in a standard kernel.
So it's not just about being fast on average, it's about guaranteeing a maximum response time. That's a key difference.
A massive difference. Predictability is the goal, which leads to the second point. Deterministic scheduling.
Deterministic meaning.
Meaning predictable.
Yeah.
You need to control the exact order and timing of task execution. You have to know when a task will run and for how long, reliably.
And Linux can do that.
Yes, GNU Linux offers various scheduling policies. Administrators can set fixed priorities, use real-time scheduling algorithms like CFO, first in, first out, or round robin, to ensure that critical tasks run precisely when needed, preventing those unexpected delays.
Okay, so a real-time kernel plus careful scheduling. Anything else?
Yes, the third piece is low-latency tuning. This is about tweaking lots of system parameters to shave off delays everywhere possible in data processing and communication.
Like fine-tuning an engine.
Good analogy. It involves things like optimizing the kernel's behavior, maybe disabling features that could cause unpredictable delays, adjusting CPU affinities, locking critical tasks to specific CPU cores so they don't get moved around.
Avoiding context-switching delays.
Exactly. And configuring interrupt handling to make sure hardware signals are processed with minimal delay. All these little tweaks add up to reduce latency and increase predictability.
It really is incredible how this fundamentally general-purpose OS, Linux, can be adapted and tuned for these extremely demanding, high-precision applications.
It shows the power and flexibility baked into its design from the start. It can be desktop, a massive web server, or a system controlling a factory robot with millisecond precision.
Truly amazing versatility. Okay, wow, we have covered a lot of ground here.
We really have.
From making systems work together reliably with clustering, to managing huge amounts of data with specialized storage, running systems within systems using virtualization, leveraging the cloud, and finally ensuring precise timing with real-time computing.
Those 5 areas really do showcase the advanced capabilities that make GNU Linux such a cornerstone in complex, high-demand environments.
It's the engine behind so much, often unseen.
Absolutely. It's the foundation for a huge part of our digital world.
So here's a final thought to leave you with. We've seen how Linux has adapted. Now, looking ahead. With computing demands always growing and totally new things like AI needing massive power, maybe even quantum computing on the horizon. What new advanced features might GNU Linux need next? What adaptations will keep it at the forefront, powering the world's most critical systems?
That's a fascinating question. How does an OS born decades ago continue to evolve for challenges we're only just beginning to understand?
Something to think about. It never stands still.